Thank you very much for your presentation, Dr. Tosha. So let me introduce the next speaker, Kasumi Yasukawa. She's joined to the Geological Survey of Japan. Currently, it's called National Institute of the Advanced Industrial Science and Technology, so-called AIST. She joined this organization in 1987, and she had studied numerical modeling of geological reservoir and ground source heat pump systems. So she has management experience at New Energy and Industrial Technological Development Organization, which is so-called NEDO, N-E-D-O, and the Ministry of Economic Trade and Industry from 2007 to 2013. She has served as a board of a director of International Geothermal Association for 2 terms. From 2007 to 2013, and has been an EXCO member of the International Energy Agency Geothermal Implementation Agreement, IEAGIA, since 2013. Currently, she is a Deputy Director of a Renewable Energy Research Center in AIST. So please proceed.
Thank you, Otomaru-san, and good morning, everyone. It's a great pleasure for me to be here as a speaker. So I have lots of slides, so I just go through my presentation. So at first I make some introduction, and then I introduce 3 research topics, and then I summarize. So my introduction is like a summary of the former speaker, Dr. Toshi Tosha, said. Although Japan is rich in geothermal energy, its utilization is very limited. So the 3 major barriers include regulations on natural parks, limit in the development in natural parks, and development risk and cost, and social acceptance. The former 2 barriers were largely mitigated by supporting policy by the central government after the nuclear accident in March 2011. But social acceptance still remains a major problem, especially due to opposition by groups of hot spring owners fearing degradation of hot springs. Therefore, to gauge acceptability of this impact on local residents and stakeholders, research related to social acceptance of geothermal development has been conducted in AIST, our institute. So at first I introduced about overall system design. It has a philosophy made by my colleagues, Dr. Soma, and this idea is system design of geothermal utilization system to maximize both economical profitability and social acceptance. So regional communities are based on stable mutual relationship through human activities such as agriculture, industry, construction, transportation service industries, etc. So household is here, and there are many industries around. And it is expressed by regional economic circulation model. This is the model. And there is no geothermal energy use yet. A balanced circulation of money, persons, and goods, etc. exists to some extent of the local region. And then, if there is some geothermal development project appears, the regional economic circulation model changes after geothermal development. Such development may take some stakeholders happy and the others unhappy, thus triggering opposition campaigns. For better social acceptance, transparency of information among all stakeholders is essential. Idealistically, for equity, system design should be agreed by all stakeholders. So a concept of overall design system, OSD, is developed. In OSD, several possible energy utilization systems is a method of utilization, such as simple flash system or binary system with heat supply system will be suggested. Detailed design of each method will be adjusted to optimize objective parameters such as business profitability and social acceptance. The best method with highest objective parameters at the time step may be chosen at each time step. The best method may vary with time because exploration result gives more accurate data on subsurface system, which are input data for OSD, and more communication may improve social acceptance that enlarges the range of acceptable methods. Thus, the best method may change several times with time step and reaches the final OSD when final decisions should be done. The OSD is based on an idea of multi-objective optimization, such as economical profitability and social acceptance. And in many cases, trade-off exists between these objective parameters. Optimal solutions on the maximum limitation line of two trade-off valuations are shown in this figure. So in this figure, this is a profitability and this is a social acceptance. And so this is a line for line of the maximum limitation line. And you can use either A or B or any points in this line to get the maximum solution for two trade-off parameters. Possible design solutions are plotted within the gray zone. So this is the This is the maximum, but this is not maximum, but still the possible solutions, acceptable solutions. And A and B are called Pareto optimal solutions, while C is merely one of feasible solutions. Pareto optimal solution can be defined for 3 or more trade-off elements. So it's only 2-dimensional trade-offs, but there are 3-dimensional or 4-dimensional trade-off plots can be made. So OSD only shows these trade-offs. Decision on choice of solution is done by stakeholders. So you need some discussions based on these things. Therefore, visualization of benefit and risk is an important role of OSD. Such tools may be developed in the future. So this OSD study is still ongoing, and we can show you some more results later. Let's go to the next thing. Next topic is geochemical investigation on relationship between geothermal reservoir and hot spring aquifer. This study is to find out hydraulic relationship between geothermal reservoir and the shallow hot spring aquifer system to find out what kind of monitoring system is more effective to avoid the influence of geothermal development onto shallow hot spring aquifer. So this figure shows a characteristic of five types of relationships. The first one, type 1, is identical thermal water. So this red or pink color shows the geothermal reservoir, and that is identical to the shallow hot spring aquifer. The second type, type 2, is seepage thermal water. In this case, there is a cap rock exists, but the cap rock is not very solid. So some part of the geothermal fluid, especially some liquid phase, can go through this cap rock. And so the shallow aquifer is just the same geothermal fluid, just diluted by the precipitation. Type 3 is steam heated type. So in this case, the cap rock is more solid, but still the gas phase can go through. So in this case, some part of the geothermal steam and gases go to the shallow part. And type 4 is heat conduction type. And in this case, cap rock is very solid and it's really impermeable. So no fluid is go through this cap rock. Only heat can go through as a heat conduction. And type 5 is independent. So geothermal reservoir and the shallow aquifer is, in geometry, it's not so close. So even heat is not related between two of them. Something important about these 5 types is that the types can be roughly estimated by the geochemical components of the shallow aquifer. So you don't need to investigate for deep geothermal reservoir, but only by shallow aquifer components you can estimate which type is it. And because of this relation between geothermal reservoir and shallow aquifer, possibility of geothermal development influence to the shallow aquifer is large in this case, and it's medium, and it's small, and it's very small, and it's none here. And not only large and small, but also the possible major influence to shallow aquifer would be flow rate in this case. And in this case, would be flow rate and dilution. And for this case, the main change would be chemical components, because if the gases are not going to the shallow aquifer, the chemical components might change. And for this case, there's no major influence. So then, the most important monitoring items would be changed, depends on these 5 types. So at first, we try to figure out which type is it by the chemical component and try to find, separate in 5 types. But then we found that it's not very successful because even though the relationship can be separated in only 5 types, the chemical component, the type of chemical component is not only 5 types, but roughly we found 7 types. So I would show you what are these 2 more types, 2 new types. And one of the new 2 types is CO2 supply type, and the other one is volcanic gas supply type. So there is a magma in the deeper part, and magma emits some volcanic gases. So volcanic gas contains HCl, SO2, H2S, and CO2. And in some cases, all these gases go to shallow aquifer directly, and then it makes volcanic gas supply type hot spring. And all these acid fluid like HCl, CO2, and H2S remains in this hot spring, making very acid hot spring. But CO2 cannot remain in this shallow aquifer because it's too acid for CO2 to stay there. So CO2 just emitted to other parts. So this type of shallow aquifer contains only CO2, SO2, HCl, SO2, and H2S, very acid. And the other cases, these gases go to geothermal reservoir. And in this case, because of very high temperature condition, water rock interference occurs, and this kind of chemical reaction changes this acid fluid into neutral pH fluid. And so these volcanic gas not remains as the same as this original style, and only So in geothermal reservoir has some neutralization effect. And only CO2 would emit from this reservoir and coming to shallower part or coming to some shallower aquifer. So part of the CO2 is directly coming from magma to shallow CO2 type aquifer, and sometimes coming from geothermal reservoir. And sometimes there are some other CO2 sources, some organic origin or something. So as a result, what happens is like this type of very acid volcanic gas supply type is independent type in 5 types of relationship. But a CO2 supply type could be any of these 5 types because sometimes there is no relation and sometimes related to geothermal reservoir. So in case of CO2 supply type, we cannot decide which relation it is. So this is a schematic figure of showing these 7 types. And this is the flow chart of type analysis. So I don't explain details, but just to show that type 1 is very Cl minus dominant type, and type 2 is also Cl minus dominant, but not as much as type 1, and CO2 supply is CO2 dominant. And type 3 is SO4 dominant, and type 4 and 5 are different ones. And I have to make one apology that here it's shown as SO4 minus, but it should be SO4 2 minus. So that is how we categorize all 7 types. And this is one of the examples to use this categorization to the real field. So we chose Co2 area because in this area there are so many hot springs and we have a lot of data. And as like the flow chart shows in the former figure, identical and seepage are rich in Cl2. So this is identical system, and orange one is seepage. So these are rich in Cl minus. And steam heated type is this green one. This one is rich in SO4 2 minus. So these are directly coming from the flow chart. But there are some other characteristics of this region. In this region, heat conduction system has lower SO4 2 minus contents than independent type. It shows that CO2 supply type is the heat conduction system is the white one. White one has lower SO4 2 minus than independent type. Independent type is purple one. So just comparison of this white one and purple one. And high temperature hot spring. The large dot shows the high temperature one, these ones and these ones. Mainly identical system, and only 2 are seepage type. So there are some characteristics of this area. And another graph is just plotting the same data to the temperature and total dissolved solids. It's how much components are dissolved in this fluid. So I just skip it. And we plot the same data to this map. And in this area, there are 3 geothermal power plants. One is Co2 Kanko Hotel power plant. It's a very small power plant, but still it's a steam turbine system. And this is the famous Hachobaru geothermal power plant. This is the largest geothermal power plant in Japan. And there's Otake power plant. And as you can see, many of the hot springs are just 1 kilometer or closer to this power plant. And in this, around this power plant, most of the hot springs are green one or orange one. That means steam heated type or seepage thermal fluid type. But there are some CO2 supply types. So that can be said that these yellow ones, these CO2 supply type might be similar to seepage thermal water or steam supply, steam heated type. But there are some other yellow ones, other CO2 supply type, and these may not be connected to geothermal reservoir. It could be independent type. So by this kind of plotting, you can find out for CO2 supply type, which is not related to geothermal system or which could be related to geothermal system. So just go to the next topic, that is development of hot spring monitoring device. So again, this newspaper article shows this is an advertisement of hot spring owners who are very much against geothermal development. And this is a full one page of the newspaper to make some negative campaign against geothermal reservoir. So one of the key issues for consensus from local community geothermal power generation, lack of scientific data to quantitatively evaluate effects of geothermal development to hot springs. So data with nature of continuous and reliable and high resolution is necessary. So now we are developing some hot spring monitoring system, hot spring monitoring devices. And so we are measuring the temperature, flow rate, and conductivity, electric conductivity. And so there are such sensors. And another feature is that wired or wireless data transmission capability and flexible interface to various types of pipes. And this is flexible power interface, AC/DC. And we developed this device and we applied for several hot springs in Japan. And so this one shows the specification of the monitoring system. And this figure shows how it looks like. This is a whole system, and it's not very large. It looks like this. And this figure shows one of the field experiments. So here there are, we measured flow rate here and here. And for this case, it's a prototype, and this is not very compact as like I showed you before, but we, preliminarily we measured with this separate system to measure the hot spring, to do the hot spring monitoring. And the result is this one. And we tried to find out the suitable sampling frequency every second or every hour or every day or something. And this dotted line shows the 24 hours average of every 1 second sampling data. And the green line shows the sampling of every hour, and blue one is every midnight, and pink one is every noon. So as you can see, the green one and dotted line has very good fitting. That means if you measure only every 1 hour, that is enough. You can see the very similar result as every second. So you don't need to measure every second, but you can measure every 1 hour. That is the result of this study. So the hot spring monitoring research is still going on. So now I summarize all our study. To gauge acceptability of this impact on local residents and stakeholders, research related to social acceptance of geothermal development has been conducted by ASSD. Overall system design is a system design concept to maximize both business profitability and social acceptance. More study is needed for its realization. Geochemical analysis of hot spring fluid may help planning of hot spring monitoring to avoid interference of geothermal reservoir operation. It may also be used for geothermal exploration. Hot spring monitoring device has been developed and applied for several domestic hot springs. Thank you very much.